Okay. Yesterday we looked at the Wiener index. And we also said that the Wiener index for Pn or the star, what was this? Okay. So these are the two things. So what we want to prove among all trees on n vertices, Wiener index d of t is at least that of equality if and only if t is equal to and d of t is at most equality both these statements we want to prove them using induction. So take small situations. So if you take a proof, so I leave checking the basis for induction to you. Now, if you take a tree on n vertices, take a leaf. This is what a leaf. Then the Wiener index of t is equal to Wiener index of t prime plus where that vertex removed. If I call this vertex as y, then the distance between x and y is 1. And for any other vertex, the distance between, if I call this, if I call this v, the distance xv is 1. And for any other w, the distance from x to that vertex is at least 2, clearly, because it passes through v. Therefore, count 1 plus 2 times n minus 2 minus 3 plus n square minus 4n, so therefore 2n plus 1. Yeah. Therefore, that says that the minimum is n minus 1 square. When do I get equality here? If I must get equality here, if so d of t is bigger than or equal to n minus 1 square. In case of equality, we must have equality everywhere. What does that mean? Every vertex in T prime except that V is at distance 2. Has distance 2 from X, and by induction T prime is a star. Which center? Yeah. So that's for the first part. Let's look at the second part. Again the same thing as there. Distance of T is equal to distances in T prime plus now I argue that this is less than or equal to T prime is a tree on n minus 1 vertices, therefore by induction n replaced by n minus 1, so n plus 1 replaced by n, that's exactly what we're doing there, the formula plus my argument now, just think about this, is that these are as many as n minus 1 positive numbers, n minus 1 positive numbers, one of which is 1, others will be 2, 3, etc., etc. And I want to maximize this now. I want to make this as large as possible. Think also, because we are working on a tree, if distance 6 occurs, suppose the distance between x and y is equal to 6, then for some other vertex the distance between x and that vertex will be equal to 5. So there are no gaps in these positive numbers. So if 6 occurs as a summand here, then 5 must also occur, 4 must also occur, 3 must also occur, 2 must occur, etc., etc. So these are sort of continuous things. It cannot be true that some summand is equal to 10 and summand 8 is missing. That just cannot be true. Therefore, to maximize this, just look at this, the picture. And then there will be branching outs. So distance here is 1, then it is 2, 2, 2. 3. It is, if you want to increase the distances, it is a better idea to shift this vertex from here to here, because that way the distance will become 4. Is that clear? Instead of 3 it will become 4. That 3 will go away and therefore you will be. So keeping the vertices as far as possible is a profitable thing. The farthest you can keep a vertex from X is n minus 1, obviously. There cannot be a vertex whose distance is more than n minus 1 because you have only n vertices here. But as we just said, these are all continuous. So if you have to have n minus 1, then you must have 1, 2, 3, 4, all the way up to n minus 1. Therefore, the maximum here is attained by which is really the Wiener index of path. In case of equality, I go over this whole argument again, okay? Then this should be as large as possible, and this becomes as large as possible by taking T prime to be a path by induction. So you have n minus 1 vertex graph for which the Wiener index is maximized by taking it to be a path. And then this vertex X is adjacent to some vertex V. But then if you want to have maximum distance, it is profitable to make X adjacent to the last vertex so that all the distances do occur 1, 2, 3 all the way up to n minus 1. Therefore, equality by induction implies that T prime is Pn minus 1 and distances from X, take all possible values, i.e. X is adjacent to an end vertex of Pn minus 1, which implies that your tree T must be equal to Pn. Okay? Now the Wiener index is a monotone. It's a monotone idea. What does that mean? Quite easy to see as a lemma. Let H be a subgraph if you take two vertices here, then their distance in H would be greater than or equal to their distance in G, because in G the G has more edges than H. Therefore, the Wiener index of H is greater than or equal to Wiener index of G. Clear? A connected graph. Then Wiener index of G is less than or equal to n plus 1, choose 3. How do I argue about this? Take a connected graph G. Look at spanning tree. Connected graphs have spanning trees. So it has a spanning tree. That spanning tree, let's call it T. if you call it T, will have Wiener index which is greater than or equal to the Wiener index of G, because it's a subgraph. Being a tree on n vertices, that theorem says that the Wiener index of that of that tree on n vertices is still less than or equal to Wiener index of path on n vertices, which is n. So this is the maximum that one can get. H must, yes, there I would agree. Yeah, because if you have less number of words, H be a spanning subgraph. All right. Thank you. Yeah, which is what we need. Spanning subgraph. That will take care of that. Yeah, must have, you're talking of the same vertex set, because if you have fewer vertices, then obviously that cannot be true. Okay. Yeah, which is what we are using here also. Okay, thanks. Wiener index in some sense indicates the scatteredness of a graph. So it is a scattered, how roughly the larger Wiener index means the graph is more scattered. Okay. And there is a big difference between a path and a star. Both are trees, but in some sense they're quite different kinds of things. This is more well knit than that. Okay, the path you can. This also, both being trees, each edge is a cut edge, etc. All that is true. But there is a difference between this and that. Namely, and that is sort of quantified by saying that that has largest Wiener index, that has smallest Wiener index. Okay, what we want to do now is a question of this kind. Given n, how many trees on n vertices? For example, if I take n is equal to 3, then this is a tree that I can draw on 3 vertices. Really speaking, up to isomorphism, this is the only tree I can draw on 3 vertices. That's clear. That's the way. It's a peculiar situation. This is a path. It's also a star. Situation where it also happens to be a star, because that's clear. That's the center of that star. If you take n is equal to 4, then you have a star. The peculiarity with a star is that that vertex has degree 3. It has degree 3. If you don't have a degree 3 vertex, then all vertices have degree 1 or 2. If a tree has the property that each vertex has degree 1 or 2, then it must be a path. Therefore, these two are extremes. They are not isomorphic to each other. When n is equal to 5, this number will be considerably larger. One is of course a star, other is a path. That is a vertex of degree 4, so all those are attached there. If I don't have a vertex of degree 4, maybe I have a vertex of degree 3. This is not isomorphic to those. And that sort of up to isomorphism, that's the only drawing I can make. I can make that vertex adjacent to that vertex, but that is no different from this. Up to isomorphism, there is no difference. Whether it's adjacent to that vertex or that vertex, there is no difference between this vertex and those 3 vertices. Okay? If you don't have a vertex of degree 3, then it means that all the vertices have degrees 1 or 2, which means it's a path like that. So those are the only 3 examples of non-isomorphic trees on 5 vertices. If you take number 6, 7, etc., then these numbers keep increasing. They keep increasing. So if I want to have a function function on natural numbers, which will give me the number of non-isomorphic trees on n vertices. This clearly exists, but there is no explicit formula. There is no known explicit formula. I mean, it clearly increases with n, that's very clear. Intuitively, it's very clear that there will be more trees on 100 vertices, but more means how many? These are tabulated. These are all tabulated. On the other hand, a relatively easier question is to look at what are called label trees. So far as label trees are concerned, this is a label tree on 3 vertices. This is also a label tree on 3 vertices. And this is also a label tree on 3 vertices. There is no orientation here. What does that mean? I cannot really redraw this so that one, I can, if I, these two are considered same. They are to be seen as the same ones. The vertices are labeled. Vertices are labeled. So up to labeling, actually there are 3 label trees on 3 vertices. Number of label trees on 3 vertices is 3. If you want to calculate number of label trees on 4 vertices, yes, we catch hold of that. And there will be 4 such, clearly, because it depends on whom I make the star. If I want to look at path, then it depends on who is in the middle. These two are not same. They are not same label trees. With a little diligence, you should be able to show that there are 12 of this kind, 4 of this kind, making a total of 16. There are as many as 16 label trees. It so turns out that answering the question of how many label trees are there on n vertices is an easier question. So the earlier situation I talked about should be called unlabeled. It is easier to answer the question for labeled than unlabeled. Labeled trees can be counted more easily than unlabeled trees. And there is a concrete answer to that question. How many labeled trees there are on n vertices can be answered. There is a concrete formula for it. Before I get to that, let's see that this question amounts to doing something which is connected but doesn't become all that apparent. What is this? This is a complete graph on 3 vertices. It's a complete graph on 3 vertices. It has spanning trees. How many spanning trees does it have? One spanning tree, of course, is 1, then 2, and then 3, which is what we have drawn there. Therefore, now the connection should become very clear. Every label tree on n vertices is a spanning tree of kn. And what is it that I do? I begin with a kn, label the vertices of that kn using the numbers 1, 2, 3, 4 up to n. As soon as I get a spanning tree, it will become a label tree on n vertices. Conversely, if I have a label tree on n vertices, it's a spanning tree of complete graph. Therefore, let's write a statement. Obvious statement. Number of spanning trees in Kn is equal to number of label trees on the label set Okay? There is a bijection. I have already told you how to. For example, this is K4. That's a spanning tree of that K4, and it's also a labeled tree on 4 vertices, 1, 2, 3, 4. This question, the second thing here, can be answered. There is a formula for which close to half a dozen proofs for this formula. So we'll write the formula down and then we'll give one proof. This is what is called the Cayley proofer. Number of labeled trees. N power n minus 2. You see, that's why I said that on 3 vertices n is equal to 3, therefore you have 3 raised to 1. There are 3 labeled trees on 3 vertices. We have already drawn them there. For 4 vertices, 1, 2, 3, 4, 4 raised to 2, which is 4 square equal to 16. 16 labeled trees on 4 vertices. We didn't draw all of them, but should be able to. If you sit down, should be able to draw all of them. As such, Cayley gets this formula quite correctly. Cayley was the one who guessed the formula correctly. Didn't completely prove it exactly in the sense we understand. He said that this follows from this and this is the correspondence, and from that it's obvious that the number of labeled trees is n raised to n minus 2. Proofer actually gave the explicit correspondence. So the proof here is based on some bijection. It's quite a clever bijection. Bijection works as follows. I give you a labeled tree on the vertex set 1, 2, 3 up to n. Using that labeled tree, you make a sequence. You make a sequence, and that sequence is called proofer code. It's called proofer code of that labeled tree. With n minus 2 entries, the number of length of that sequence is n minus 2. The entries take values in the set 1, 2, 3 up to n, and this is a bijective correspondence. Then we argue that the number of such sequences, there are n minus 2 places, and each place can be filled in n ways. Therefore, it is n multiplied by n minus 2 times. Therefore, that number is n raised to n minus 2. And that gives us the proof of that. So this depends on the idea of proofer code. Given a label tree, on the set we construct a sequence this is called the proof or code. We'll write this down explicitly, but let me begin with an example. So n is equal to 9 here. Therefore, I am going to get a proof or code that contains 7 entries. Let's see how to go about it. This given tree has leaves. Any tree has leaves. In fact, as I see here, there are 3 leaves here. 4 is a leaf, 8 is a leaf, 9 is also a leaf. Among these leaves, the smallest label is 4. Among these, in the available ones, the smallest label is 4. What the algorithm tells you to do is remove this leaf along with that pendant edge and write the name of the vertex, write the adjacent to that leaf. So that thing is removed. In fact, I am going to remove that edge. Essentially 4 will not exist from this point on. Now I have a tree with only 8 vertices. Okay? Which of course, again for the same reason, must have leaves. The leaves here are 3, 9 and 8. Make sure you understand this clearly. 3 was not a leaf earlier. In the original tree, 3 was not a leaf. 8 and 9 were leaves, but 3 was not. 3 has now become a leaf. And 3 happens to be the smallest leaf. Repeat this process, remove. And what do I write here? The label of the vertex adjacent to that. Okay? Next, 7, 8, 9 are leaves. Among them, 7 is the smallest label. The vertex adjacent to 7 is 2. Therefore, you write 2, don't write 7. Next, 8 and 9 are leaves. In fact, it has only 2 leaves. 8 is the smallest. Remove. What do I write here? I write 5. Next, 5 is the smallest label. Remove the edge 5, 6. Write 6. 6, 2, 1, 9. 6 and 9 are leaves. 6 is the smallest. Therefore, write 2. 2, 1, 9. 2 is the smallest. Remove the edge 2, 1. Write 1. At this point of time, I have realized that I have as many as 7 entries. Therefore, I close this here. Leaving that one edge there as it is. This will be left out. This will actually be left out. Okay? Okay, just let's take one more example just to see that we get this all right. Three, 4, 7. Yeah, that's it. Yeah, we exhausted all. Yeah. Can you tell me what the proof or code of this will be? What will the first entry? 6. Is that clear? 1. Huh? Sorry? Huh? 2 is a leaf, yeah, so I should be writing 1. Yes, thank you. What happens then? This is gone. Then 6. Then 8. Yes, because for then then 7, 6, 9, 1, and that's it. Now 1, no, there is 8 also. Okay, so 7 is the smallest leaf here. At this point of time, 7 is the smallest leaf. You remove. Then I am left with 6, 9, 1, 8. What do I write? 9. Then I am left with 9, 1, 8, and 8 is the smallest leaf, therefore I write 1. And I will be left with the edge 1, 9. Okay? Is that clear? So this is a sequential procedure. It's quite a well-defined sequential procedure. Let's write this out. Let A1 be adjacent to B1. And remove. We then repeat this process. To obtain B2, B3, and will be left with just one edge. Okay, let's take one more example. Four, 1, 2, 5. Okay. Therefore, it's clear that the proof for correspondence is well defined. That's clear. The proof for correspondence is quite well defined. You know how to obtain that sequence. As always, it is the reverse direction which is not very obvious. Conversely, given proof for code, I should be able to say where did it come from, which tree did it correspond to. So let's sort of take it as a challenge how to construct the inverse of this function, combinatorial inverse of this function. So let's take n is equal to 9, B1, B2, B3, B4 up to B7. I now want to construct a tree whose proof or code will be that. Let's see how to go about it. As you see, this is the key to think about it. This is one of the most beautiful combinatorial correspondences that has been discovered in the last 100 years. Look at how B1 was found. How did you get to that entry B1? We said that look at the smallest label of leaf, that is A1. A1 happens to be adjacent to B1. Then you remove the edge A1, B1, which actually means A1 is a leaf. A1 is a leaf in the original tree. A1 is actually a leaf in the original tree, and A1 would not find a place here at all. Or for that matter, no leaf will find a place here. Because leaves will be scanned one after the other, therefore leaves cannot find places here. Anything that is a leaf, in order to write it, it has to have a neighbor which is also leaf. Okay? Therefore something that is a leaf will not really be found here. There are lots of things that will be missing here. That's very clear because there are only 7 entries here, whereas n is equal to 9. In fact, at least 2 entries will be missing. Even if they are all distinct, at least 2 entries ought to be missing from the list. From 1, 2, 3 up to 9, you are writing only 7 numbers. Therefore, at least 2 are missing. Who are all missing? 2 is missing. 6 is no. 3, 4, 5, 6, 7, 2, 7, 8, 9, they are all missing. Okay? Among them, the smallest is 2. Therefore, the first edge that I deleted must have been 2, 3. Okay? That is the way I argue. Now think of it. What's the sort of right analogy? If you know answer to the question, then you try to construct question. Sometimes you look at the end of the book and then you try to see what the question might have been. That's exactly what we are doing. What the question could have been. So it was the edge 2, 3 that was there, and this was the edge that was first shelled out. This was the edge that was cut off first. Having done that, really speaking, 2 will not have any role after this. So the tree, the partial tree that only one edge has been constructed. Look at those things here that appear only once. 3 appears here. Look at this situation. How many times will I be writing 6 here in this, for this? Once for 3 and once also for 6. Once also for 7. Not really. Is that okay? 6 has degree 3. The degree of 6 is 3. Therefore, the number of times it is written here is 2. If the degree of a vertex is a d, then in the proof or code, it will get written d minus 1 times. 1 less. If the degree of a vertex is equal to 1, which means it is a leaf, it will not be written in the proof or code at all. It will not find a place in the proof or code. It will have no place in the proof or code. So anything that is missing in the proof or code is of course a leaf. There is no question about that. So this clearly has lots of leaves. But look at this vertex like 3. This is written once. What that means is its degree in the original tree must have been 2. When I removed that edge 2, 3, after removal of that edge 2, 3, I got a smaller tree in which 3 became 3 actually became a leaf. 3 was not a leaf to start with, but 3 became a leaf in the prune tree. In the smaller tree, 3 became a leaf. And that is the available label here. Therefore, I should make 3 adjacent to 6. Next, 2 is gone, 3 is gone, 4, 5, no way, 6, yes. 6 is now available. 6 is now available. The degree of 6 is 2. 1 is gone here. Who are all gone? 2 not available, 3 not available. Degree of 1, as I just said, is 2. 1 has now become available. Therefore, I should be writing 1 here. 1 is gone, 2 is gone, 2, 3, 4, no, 5, no, 6, 7. The way I will construct this is, this fictitious second line or whatever, this is B1, B2, B3, B7, A1, A2, A3, A4, A5, A6, A7, all A's are different. They're all different because these are the vertices that will be thrown out. They have to be different. Vertex that is thrown out in the previous thing cannot be equal to the vertex that is thrown out later, because whatever vertex has been thrown out is thrown out. Okay, it cannot be thrown out again. Therefore, the second line, unlike the first line, consists of distinct numbers. It has to consist of distinct numbers. In addition, on the second line, I will not, it consists of distinct numbers, therefore it will consist of n minus 2 numbers. Exactly. No repetitions on the second line. First line may have lots of repetitions. There are. So on the second line, 2 numbers will be missing. What are they? 4 and 9. That was the age that was left out. Therefore, let's draw this tree. And then we can check that had we begun implementation of Prupur algorithm, we would have gotten the same thing. So 3 is adjacent to 2. 3 is also adjacent to 6. 6 is adjacent to 1. 1 is adjacent to 5. Lots of vertices are adjacent to 5. 7 is adjacent to 5. 8 is also adjacent to 5. 5 is adjacent to 4. And the missing vertices are 4 and 9. 4 and 9, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4 and 9. Let's see if I had begun implementation of the Prupur code here without looking at that. What is it that I would be? This will be thrown out first. This is the first one to be thrown out. Therefore, I will be writing a 3. Having done that, 3 becomes a leaf. Therefore, I will be writing 6. Having done that, 6, 7, 8, 9 are leaves. 6 is a leaf. Therefore, I will be writing 1. Then 1, 7, 8, 9 are leaves. Therefore, I'll be throwing off 1 and will be writing 5. Then 7, 8, 9 are leaves. 7 is the smallest. Therefore, I'll be writing a 5. Then 8 and 9 are leaves. Therefore, I'll be writing a 5 again. Now you're left only with 5, 4, 9, out of which 5 is a leaf. Therefore, you'll be writing a 4. And that leaves you with the edge 4, 9 as the last edge. Okay, that's exactly the same thing that we. Okay, so this establishes a one-to-one correspondence. This establishes a one-to-one correspondence between set of all label trees on vertex set 1, 2, 3 up to n and set of all sequences whose length is n minus 2 on the set with entries coming from the set 1, 2, 3 up to n. Okay, let's take one more example. Is it clear? These numbers can be really written arbitrarily. There is no restriction. It's just that they have to be n minus 2 in number. That's all. Other than that, they can all be different. They can all be even same. Okay, begin. This should be 1 because 1 is a missing number here. This should be 1. What should this be? Not 2, because 2 does, this is a look ahead policy. 2 does occur there, therefore this should be 4. Not 8. At this stage, 2 has become available. 2 has become available, therefore I better write 2. At this stage, 3 has become available. Let's draw this. 1 is adjacent to 2. Have I? Sorry, say that again. No, 6 is, yes, of course, the error occurred right there. Thank you. Yes. 5 is fine. I should have written 7 here. Of course, I should have written 7 here. I should have written 8 here. 2. What do I write here? 1, 2, 3, 4, 3 becomes available. Okay. Let's draw this tree. 1 to 2. 2 to 5. 2 also to 3. 3 to 4. 2 to 5. 3 also to 7. 2 to 8. 3 to 2 is drawn. 3 to 6. And what is the missing thing here? 1, 2, 3, 4, 5, 6, 7, 8, 6 and 9. Okay? Now let's argue. If I had started proof or algorithm here, I would be throwing off this leaf, writing 2, which is what I did there. Fine. Then the leaves are 8, 5, 9 and 7. 5 is the smallest. Oh, there is also 4. Therefore you wrote 3. That's fine. Then the leaves are 8, 5, 7 and 9. 5 is the smallest. Therefore you wrote a 2. Then the leaves are 8, 7 and 9. Smallest is 7. Therefore you wrote a 3. Then the leaves are 8 and 9. Therefore, you wrote a 2 there. Then the leaves are 3, 6, 9. Therefore, 3 is the smallest. Therefore, you wrote a 3 is the, therefore you wrote a 6 here. And that's it. Leaving us finally with the edge 6, 9. Okay. All right. So this is the proof for correspondence. Yeah. Surprising thing is it works. It works very, very neatly. What about the proof for code for this? What about the tree? Star? Yes, 3 will be 4 plus 3 equal to 7. So 3 will have degree 8. This is a star. 3 is adjacent to all. And then you will be shelving them one after the other. So that's exactly what that is saying. Okay? So 3 is the center of that star, and one by one you'll be leaving these things out. Now, Let's write what we do for the reverse direction. Given as follows. A1 and is smallest. With that property. So this is actually leaf. A1 is the leaf. This is the first leaf to go out. This is the very first leaf that will be thrown out. Having found A1, A2, what property should A2 have? A2 is not equal to A1 because A1 is already gone. There is a look ahead policy here. A2 should not be equal to any one of B2, B3 up to and is smallest with that property. Having found A1, A2, A3 up to AI plus 1 is not equal to A1, A2 up to AI, BI plus 1, smallest with that property. That's exactly what we have been doing. Make edges A1 B1, A2 B2, AN minus 2 BN minus 2. So this will give me as many as n minus 1 edges exactly. These edges are distinct. How do I know they are distinct? Can it so happen that A1 B1 or A2 B2 is equal to A5 B5? Not really, because A5 is not equal to A2. Choice. I mean, can it really? So I'm just giving an informal idea. A2 B2 equal to A5 B5. A5 is not equal to A2. Therefore, A2 then will have to be equal to B5, which is not true. The choice that we made, A2 is chosen in such a way that A2 is not equal to B2, B3, B4, B5, etc., etc. So A2 cannot be equal to B5. So this is impossible. A2 is neither equal to A5 nor equal to B5. Okay? Therefore, these edges cannot repeat. So we get exactly n minus 1 edges. A's are all distinct by choice. To say that it is a tree, all you need to see is that it is not a There is no cycle. So we'll break for a few minutes and then we'll see. Clearly A1 does not repeat anywhere, therefore A1 must be a leaf. There cannot be a cycle that contains A1. Clearly, it is a leaf in whatever you draw. It is a leaf. A1's degree will be equal to 1. Therefore, there cannot be a cycle that contains A1. Same thing we'll argue for the next stages and so on. Okay.